This video is a walkthrough of the elbow-opt.m MATLAB program. Sum of stresses is the cost function. Download elbow-opt.m and sum of stresses.m, put them in the same folder on your computer, and run the main program. You should get this result in MATLAB. This program is divided up into sections using the %% space. These portions of the program are called cells. MATLAB lets you run a section at a time or run a section and advance to the next section. This section sets up MATLAB with formatting, clearing, setting global variables, and setting some other variables. This section sets some of the variables that we're not using to the empty square brackets. The next few sections set up the equality constraints AEQ times F equals BEQ. This comes from the MATLAB help for the fmincon function. We have to supply fmincon with all these input arguments. Some of them are empty. A and B are empty because we're not using inequality constraints in this project. AEQ equals F times BEQ is the equality constraint. This is how we code our set of equations. We've got one equation for a moment balance and two equations for the X and Y force balances. The moment arms are ABIC, ABRA, and ABRD in centimeters. Row vector A contains all three. TBIC, TBRA, and TBRD are the angles theta. Capital T contains all three in radians. S computes the sine of those angles, and the moment arms are the element by element product of the insertion distances times the sines of those angles. If you double-click moment arms and press F9 on the keyboard, and then look at the MATLAB command window, you'll see the moment arms displayed. If you want, you can format, short, and then up arrow to moment arms again, and see the moment arms with fewer decimal places. AEQ is the matrix of coefficients. It's 3 rows and 5 columns. This code builds that matrix. Some of the values are 0. This section of code builds the equality constraints and the right-hand side BEQ. BEQ is 3 rows and 1 column. These are constants. This section sets lower bound to be 0 for muscle forces and sets upper bound to empty brackets because we're not using upper bounds. Nonlinear constraints are not used either. We set the options to use the SQP algorithm for it inside the fmincon. We have to supply fmincon with an initial guess. This line sets an initial guess of tens for all of our variables. If we highlight F0 and press F9, you'll see in MATLAB that this is a column vector of just 10. That's a starting guess for the forces. Here is the heart of our program, the call to the fmincon function. Fmincon outputs the force and these other values, fval and exit flag. Some of these inputs, as I said, are empty, but we have to leave them empty in here so that we can add the options. The options, remember, sets the algorithm to SQP. The remainder of this block displays the output. This block also displays the output. Field spec is used in the sprintf function to format the output. This code also contains the results of this optimization using muscle stress to the third power. Our optimization in this example uses sum of stresses, coded here in the cost function. This is a simple sum of stresses. Your task is to repeat this project with sum of stresses cubed.